Welcome, everyone. Today, we're going to explore something fundamental in algebra, linear equations in two variables. I'm excited to guide you through this topic, which is essential for understanding how equations work in two dimensions. We'll look at what these equations are, how to interpret them, and some key concepts associated with them. So, let's dive in and discover the fascinating world of linear equations together. Welcome to Slide 2. Today, we'll be exploring the contents of this presentation, starting with an introduction to the key concepts. Then, we'll dive into linear equations, understanding what they are and how to solve them. We'll look at how the graph of a linear equation in two variables looks, which helps us visualize these relationships. Moving on, we'll examine equations of lines parallel to the x-axis and y-axis, highlighting their special properties. Finally, we'll wrap up with a summary, a question bank for practice, and conclude with some thank yous. Throughout this session, we'll connect each of these topics to build a clear understanding of linear equations and their applications. Let's take a closer look at this table. Here, we have some examples of equations along with their left-hand side, or LHS, and right-hand side, or RHS. For instance, in the first row, the equation is 4x plus 3 equals 5. The LHS is 4x plus 3, and the RHS is 5. This helps us clearly see what each side of the equation looks like. In the second row, we have 2x plus 5y equals 0, where the LHS is 2x plus 5y, and the RHS is 0. The third example is minus 2x plus 3y equals 6. Again, the LHS is minus 2x plus 3y, and the RHS is 6. Moving to the second table, we see a different way of presenting equations, using coefficients and constants. For example, in 2x plus 3y equals 9, the coefficients are 2 and 3, and the constant is minus 9. This format makes it easier to identify the parts of the linear equations and helps us understand their structure better. Connecting this to our overall theme, understanding the LHS and RHS of equations is fundamental for graphing and solving them. It allows us to visualize solutions more effectively and see how the variables relate within the equations. Let's talk about linear equations. A linear equation is an algebraic equation where each term is either a constant or the product of a constant and a single variable. Think of it as a simple relationship involving one or more variables, but with no variables multiplied together or raised to powers other than 1. These equations are quite common in applied mathematics because they model many real-world phenomena naturally. What's really interesting is that even some complex, nonlinear equations can often be reduced to linear form by assuming that the quantities involved don't vary too much from some baseline or background state. This simplification makes them much easier to analyze and solve. For example, take the equation x plus 2 equals 0. If we solve for x, we find that x equals negative 2. That straightforward solution illustrates the core idea of linear equations: simple, direct, and easy to work through. So, understanding linear equations is fundamental because they're not only common, but also serve as building blocks for more complex models in applied mathematics. Now, let's talk about the solution of a linear equation. Every linear equation has a unique solution, and that's because there is only one variable to solve for. However, when we have a linear equation involving two variables like x and y, the notion of a solution changes a bit. In this case, a solution isn't just a single number, it's a pair of values, one for and one for y, that satisfy the equation simultaneously. Let's look at an example to make this clearer. Suppose we have the equation px equals 2x plus 3y. If we set equal to 3, we can substitute that into the equation. So we write 2 times 3 plus 3y equals 12. Simplifying, we get 6 plus 3y equals 12. To solve for y, we subtract 6 from both sides, leaving us with 3y equals 6. Dividing both sides by 3, we find y equals 2. So when is 3? Y must be 2 to satisfy the equation. Therefore, the solution to this particular case is the pair 3, 2. This illustrates that, in the context of two-variable equations, solutions are often represented as coordinate pairs, showing the specific values of x and y that work together to make the equation true. This concept is fundamental because it helps us understand how solutions form a set of points, often a line, on the Cartesian plane. Now, let's take a closer look at the graph of a linear equation in two variables. As you can see, this graph is a visual representation of the linear equation itself. It helps us understand how the solutions to the equation are related spatially. The key point here is that every point on this line satisfies the equation. So, if you pick any point on the line, the coordinates of that point will make the equation true. This is really important because it connects the algebraic form of the equation to a visual, geometric form. By understanding this graph, we can better grasp how changes in the equation affect the line, and how the line's position relates to solutions of the equation. This is a fundamental concept that ties together the algebraic and graphical perspectives of linear equations, which is essential as we move forward in understanding more complex systems. Let's take a closer look at this graph. Every point whose coordinates satisfy the equation actually lies on the line shown here. Conversely, any point that is on the line is a solution to the equation. So, if you pick a point on the line, it satisfies the relationship set by the equation. Now, points that do not lie on this line, those are not solutions of the equation. They don't satisfy the relationship and therefore aren't part of the solution set. This visual really helps us understand how the equation connects to the graph. And remember, the equation x plus 2y equals 6 can be represented graphically, giving us a clear picture of the solutions. This connection between algebra and geometry is fundamental in understanding how equations translate into visual representations. Let's take a closer look at how to represent equations of lines that are parallel to the x-axis. In this example, we have the equation 2y plus 3 equals 0. Now, the first step is to understand what this means graphically on the Cartesian plane. Since the line is parallel to the x-axis, it will be horizontal, meaning it has a constant y value for all x values. To find that y value, we solve the equation for y. So 2y plus 3 equals 0, subtract 3 from both sides, giving us 2y equals. Then, divide both sides by 2, and we get y equals minus 3, 2. This indicates that the line is horizontal at y equals minus 3, 2. Now, when we represent this on the number line, or more accurately on the Cartesian plane, we draw a horizontal line crossing the y-axis at y equals minus 3, 2. The key point here is that lines parallel to the x-axis always have the same y value, regardless of the x value. And this concept is fundamental because it helps us understand how equations translate into graphical representations, connecting algebraic expressions to their visual forms. So, whenever you see an equation like y equals a constant, you know it's a horizontal line parallel to the x-axis. Let's look at example 1. Here, the solution involves the equation 2y plus 3 equals 0. This equation has a unique solution, which means there's only one value of y that satisfies it. When we think about this geometrically, we're essentially plotting the equation y equals minus 1.5 on a number line. Visualizing it this way helps us see exactly where the solution lies. The key point here is that linear equations like this one typically have a single solution, and representing that solution on a number line makes it easier to understand and confirm. This example ties into our overall theme of understanding solutions, both algebraically and visually, emphasizing the importance of geometric interpretation in solving equations. Let's talk about the equations of lines parallel to the y-axis. These lines are special because they run straight up and down, parallel to the y-axis itself. When we write an equation like x equals a constant, such as x equals 2, we're describing a vertical line that stays fixed at equals 2. For example, if we take the equation 2x plus 9 equals 0, we can solve for x and find that x equals minus 4.5. This means that the line passes through the point, minus 4.5, 0, and it's parallel to the y-axis. The key takeaway here is that equations of the form x equals a number represent lines that are vertical, and they don't depend on y at all. They extend infinitely up and down along that fixed x value. Understanding these lines helps us see the geometry of the coordinate plane more clearly, especially when we're analyzing graphs or solving equations involving vertical lines. Remember, these lines are essential in understanding the structure of various equations and their graphs, fitting perfectly into our overall theme of understanding line equations in the coordinate plane. Let's wrap up with a quick summary of what we've learned about linear equations in two variables. An equation like x plus by plus c equals 0, where a, b, and c are real numbers and not both a and b are 0, is called a linear equation in two variables. This is important because such equations represent straight lines on the coordinate plane. Now, one key point to remember is that a linear equation in two variables has infinitely many solutions, since every point on the line satisfies the equation. For example, the equation equals 0 represents the y-axis, while y equals 0 represents the x-axis. These are special cases of linear equations that define the axes themselves. When we graph equations like y equals a, where a is a constant, we get a straight line parallel to the x-axis. Similarly, the graph of equals a is a straight line parallel to the y-axis. These horizontal and vertical lines are fundamental in understanding the geometry of linear equations. Another important concept is that the graph of every linear equation in two variables is a straight line. This consistency helps us visualize and analyze relationships between the variables easily. Finally, an equation like y equals mx, where m is the slope, represents a line passing through the origin. This form highlights the slope-intercept relationship and emphasizes the line's passage through the point 0. All these points tie together to give us a clear picture of how linear equations shape the geometry in the coordinate plane. And understanding these basics is essential for exploring more complex algebraic and geometric concepts. Let's go through some key points from this final slide. First, we have the task of expressing linear equations in the standard form, which is x plus by plus c equals 0. For example, when we have x equals 3y, we rewrite it as 1x 3y plus 0 equals 0, so here a equals 1, b equals, and c equals 0. Similarly, for 2x equals minus 5y, rewriting gives 2x plus 5y plus 0 equals 0, with a equals 2, b equals 5, and c equals 0. And for 3x plus 2 equals 0, we write it as 3x plus 0 y plus 2 equals 0, so it is 3, b is 0, and c is 2. Next, let's look at solutions of the equation 2x plus y equals 7. We can plug in different values for x and y to find solutions. For example, when is 0, y must be 7. When is 1, y is 5. When is minus 1, y is 9. And when is 2, y is 3. These are all valid solutions because they satisfy the equation. Now, moving to the concept of finding the value of k in the equation 2x plus 3y equals k. If we know that x equals 2 and y equals 1, we substitute these values into the equation. So, 2 times 2 plus 3 times 1 equals k, which simplifies to 4 plus 3, giving us k equals 7. This shows how specific points help us determine the constant in a linear equation. Finally, let's look at graphing these equations. For y equals 4, we can plot points like 0, 4, and 4, 0. Similarly, for y equals 3x, points like minus 1 and 1, 3 help us visualize the line. These graphs are essential because they give us a visual understanding of how the equations behave in two variables, tying everything back to the overall idea of understanding linear relationships.